Welcome PCS members and our friends to our today's seminar. It's a great pleasure to have with us Dr. Raditya Bomantara from University of Sydney. And I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Thanks, Stephen, and also welcome to everyone. And thanks, Raditya, for offering us this opportunity to listen to your talk. Let me just be quick. We were a bit late here with ringing the bells. So Raditya has done his undergrad studies at the National University of Singapore, and then he continued at the same university up to obtaining his PhD, or as it's called there, Doctor of Philosophy in Physics. And his research areas are theoretical condensed matter physics, quantum computing, quantum control. And he did his PhD with Professor Jiangbin Gong, whom we know very well, here also at the center. And since 2000, so he finished his PhD in 2017, and since 2020, he is a research fellow at the School of Physics, University of Sydney, Australia, where he, as far as I can understand, has an independent research fellow position. He has quite a steep and interesting and impressive publication curve, and he is active in such phases, in such parts of physics as quantum kicked systems, Floquet physics, but also quasi-periodic systems and topological insulators, superconductivity. I find here on the first page of his Google Scholar page, Dirac cones, and other buzzwords, which are all familiar to us, and in particular also time crystals. And this is why we invited you to give us a talk today. And so therefore we are looking forward to learn news about constructing large period discrete time crystals with quantum repetition codes. Please, Raditya, the floor is yours.
Okay, so thank you very much, Sergey, for the very detailed introduction and also for the invitation to give a seminar here at PCS. So it is really my pleasure also to be able to share with you this work that I did earlier this year about basically a general recipe to create time crystals by borrowing some machinery from quantum repetition codes. So yeah, for those of you who are not familiar with these two terminologies, time crystals and quantum repetition codes, there is no need to worry, because along the way I will also explain these two concepts accordingly. All right, so okay, so in order to be able to understand the concept of time crystals, so let me first quickly explain the concept of spontaneous symmetry breaking. And this is best illustrated in this picture. So imagine a particle under the influence of this potential. So we can see that the Hamiltonian associated with this potential will be invariant under any rotation in the XY plane. However, the ground state of such a system, which corresponds to a particle occupying like the bottom position, here will not be invariant under such a rotation. You can imagine, for example, if the particle is somewhere here, if you rotate in the XY plane, then it will clearly move to another location that we can distinguish from the original location. Okay, so this phenomenon of spontaneous symmetry breaking has also underlined many physical phenomena, which include the formation of space crystals, which spontaneously break space translational symmetry, ferromagnetic materials, which break rotational symmetry, and so on. And with that in mind, we can now understand time crystals as basically phases or materials which spontaneously break time translational symmetry. So based on what I mentioned in the previous slide about spontaneous symmetry breaking, we can immediately see that time crystals should be impossible to achieve in static systems, because that basically means that we can find a system whose ground state exhibits some time dependent behavior, but that basically will represent some sort of a perpetual motion, which violates the second law of thermodynamics. And in fact, this impossibility of time crystals in static systems have also been rigorously disproved in these two PRLs. However, in 2015 and 2016, two groups have independently proposed the possibility of having time crystals in time periodic setup. So these time crystals are called discrete time crystals. But in this case, the definition of discrete time crystals will be more subtle because, for example, the notion of ground state is not exactly well defined in the time periodic setting. So for the purpose of this presentation, we can basically just understand discrete time crystals to have the following three properties. So the first property here is basically the demonstration of time translational symmetry breaking, as we expect for the original definition of time crystal. So in the time periodic setting, we can basically imagine something like a system that we drive at a certain driving period of big T, for example, and then we should be able to find an observable that displays a periodicity at an integer multiple of the driving period. Okay, so that's the first property. And then for the second property, we also require that this periodicity should not be a result of some fine-tuning of system parameters. So as an example, if let's say we can find a particular system whereby a certain observable is periodic at 2 times the period of the driving, then if we tune the system parameter slightly, then the same observable should approximately display 2T periodicity and not some other periodicity. And then the third property here basically means that this periodicity of the observable should persist for a very long time that increases with the system size. Okay, so to give an illustration, let me give you an example of a not discrete time crystal. Okay, so to do that, let's consider basically just a single spin half particle subjected to this Hamiltonian, where basically you apply nothing, except that after every regular interval of big T, you apply a spin rotation about the x-axis. So here x means the Pauli x operator. Okay, and then suppose we tune this value of h to a particular pi over 2, and then we prepare the state to be initially in the spin up position, and then we can see that the dynamics of the system will go as illustrated in this picture. So basically, the system starts in the spin up position, and then it will stay there until time big T, and then because of the kick of due to the Hamiltonian, the spin will flip, and then it will stay there for another duration of big T, and then it will flip back to the original state, and so on. So here we can see, therefore, that the Hamiltonian has a periodicity of big T, but the system, I mean the particle has the magnetization has a periodicity of 2 times the driving period. So this seems like a time crystal, but actually it's not really a time crystal, because this 2T periodicity is a result of the fine-tuning of h. So we can imagine, for example, that if we just slightly deviate this value of h from pi over 2, so that means that basically after one period, the rotation will not be exactly 180 degrees. We can see that the particle, the magnetization of the particle will still be periodic, but the periodicity will be completely different from 2 times the driving period. Okay, and therefore by the properties number 2 and number 3 of discrete time crystals in the previous slide, this particular example is not a time crystal. All right, any questions so far up to here? Okay, so if not, now what is an example of a discrete time crystal? So it turns out we can modify the previous example slightly. So rather than just having a single spin half particle, we can instead have a number of spin half particles. And we also modify the Hamiltonian such that the Hamiltonian now is a 2 time-step process, whereby during the first half of the period, all the spins are subject to this spin-spin interaction, and then during the second half of the period, each individual spin is subject to the spin rotation about the x-axis as before. Okay, and then again, let's assume that all the spins are aligned in the positive z direction. Okay, and then we define, we look at the average magnetization of all the spins. So again, if we fine tune this particular value of hj, we can make the rotation to be a perfect 180-degree rotation, and then we can see that after one period, the spin will flip, and then it will return to it will return to the original position after 2 periods, and so on. So again, we have a dynamics that is 2 times the period of the driving period. Okay, but the main difference between this example and the previous example is that this 2T periodicity is rather insensitive to the choice of tuning this parameter to a specific value, because as we can see on the right panel here, so if we just tune this h slightly from the ideal value, we can clearly see that the average magnetization will still oscillate roughly between 1 and -1 for the case when big N equals 4 and big N equals 8. And moreover, we see that when we increase the system size, so that means we look at N equals 8 here, this 2T oscillation persists for a longer time as compared with N equals 4. Okay, so this clearly demonstrates properties number 2 and properties number 3 of discrete time crystals, and therefore this example represents a genuine time crystal. Okay, now when I presented to you this Hamiltonian, it might seem that this Hamiltonian is a bit artificial, because basically you have something that radically change at a specific time, but actually this particular Hamiltonian has been realized in various experimental platforms. For example, in trap ions, they can even further split the first 2 terms here to achieve a Hamiltonian that switches between 3 terms, as we can see from the left panel here. And then they also evaluated the magnetization dynamics, so similar to what I explained in this slide. Yeah, and picture P here corresponds to the case when you don't have interaction. So when the interaction is turned off, so we can clearly see that the dynamics is chaotic, whereas if you turn on the interaction, then 2T oscillation can clearly be observed here. Okay, and then some other experiments also include NV centers, as well as recent as this year, this time crystal has also been realized in the emerging Sycamore superconducting circuit. Okay, so any questions so far? Now, so the previous successful experiments that I have introduced deal only with subset of discrete time crystals that involve observable with 2T dynamics, right? As we can see from all these pictures. So we can basically see magnetization that oscillates between 2 values. Okay, however, time crystals can be more general than that, right? So we, based on the definition that I mentioned at the beginning, we should also expect the possibility of discrete time crystals whose observable can actually display periodicity that can be any integer multiple of the driving period. And being able to create such time crystals will be especially useful if we want to further explore the full potential of such phases. For example, if we want to study the analogs of condensed matter phenomena in the time domain, or even more ambitiously, if we want to harness the potential quantum technological applications of time crystals, then it will be necessary to be able to create general time crystals with higher periodicity. Okay, so in fact, there are already some theoretical work on this along this direction, where they propose time crystals with with higher periodicity. But so far, these theoretical works require the use of particles that have large degrees of freedom, like boson or parafermionic particles, and therefore these proposals can be non-trivial to realize in experiments. And with that in mind, so I can now tell that basically what I accomplished in the paper that I'm about to explain in the remaining slides is that I can actually propose to create these more general time crystals using only spin-half like particles. And the main idea is actually to use some machinery from quantum repetition code. Okay, so any question up to here? And of course, before I explain my general construction, I believe that maybe not all people in the audience might be familiar with this quantum repetition code. So I also have prepared like a single slide to explain what this is. So basically, quantum repetition code is an example of a quantum correction code. So generally, the way quantum error correction code works is like this. So you want to encode a qubit, but you want to be able to detect and also correct errors occurring on this qubit. So how can we do that? So we do that by encoding our qubit using multiple qubits instead. So these multiple qubits are called physical qubits. So for example, our qubit can comprise of n physical qubits, each of which can be labeled by Pauli matrices Z and X. And we can label these physical qubits through index 1 through n. But the thing is, since we want to encode a qubit, which is a two-dimensional is a two-dimension in Hilbert space, whereas n physical qubits have 2 to the power of n dimension, we need to put some constraint on the system. And to do that, we can define the so-called stabilizer operators, which are basically mutually commuting operators that in the case of quantum repetition code, we can choose these stabilizer operators to be a product of 2 Pauli Z operators between neighboring qubits. And then the idea is that we encode our quantum information in the logical subspace, defined as the subspace where all the stabilizer operators set to 1. This can be done because, again, by construction, stabilizer operators are mutually commuting. Okay, so and then within this two-dimensional subspace, we can also define the analogs of Pauli Z and Pauli X called the logical operators. So in the case of quantum repetition code, the logical Z operator is basically just the same as the physical Z operator acting on any of the qubits, whereas the logical X operator actually comprises of the product of all the physical X operators. So you can, for example, directly verify that this logical Z and logical X indeed satisfy the algebra of the Pauli matrices. And then we can also define the logical basis states for this quantum repetition code, similar to how we define the computational basis state for a normal qubit. For example, that we define 0 state and 1 state to be the eigenstate of the Pauli Z operator. So we can also do that here, but remember that we also have this constraint that the 2 states should also simultaneously diagonalize all the stabilizer operators with this eigenvalue of 1. And as a result, we can define the logical 0 and the logical 1 to be a product of physical zeros and product of physical 1s. Hence the name quantum repetition code. So the way this quantum error correction code works is that basically, if there is an error occurring in the system, then this error will flip some of the stabilizer. I think we lost the connection. Oh, really? Hello?
I don't see any problem. Hello? Raditya?
Yeah, I also have no problem.
Hello?
Yeah,
So,
we can hear you.
okay,
guess,
so
Perhaps
just
it's
now I
Sergey's.
think.
I guess
I
Sergey.
see. So should I just continue?
Yes, I guess so.
Okay, right. Yeah, so where was, oh, okay.
What happened?
Right.
Sergey, I think you have some issues with connection, maybe.
Well, I was kicked out somehow. Let's
okay.
continue.
Okay. All right. Yeah. So so the way quantum error correction code works is that if there is an error occurring in the system, so for example, if we apply like a single physical Pauli X or Pauli Z on any of these two qubits, or a superposition of them, then we can clearly see that the stabilizer operators, some of the stabilizer operators will be flipped from +1 and -1. And therefore, by measuring the stabilizer operators, then we can see what kind of error has occurred, and then we can respectively correct the errors. For the purpose of this presentation, we are actually more interested in something called passive quantum error correction, or in other words, the hardware implementation of quantum error correction code. So to do that, basically we can prepare a Hamiltonian comprising of all the summation of all the stabilizer operators of a quantum error correction code, in this case, quantum repetition code. And the idea is that the ground state of this Hamiltonian will contain these two logical basis, the logical basis states 0 and 1, and any error that changes the stabilizer eigenvalue will be energetically penalized. Okay, so yeah, any questions so far about the introduction to quantum error correction? Okay, so if not, then now we can revisit this existing 2T periodic discrete time crystal model again before I present my general construction. Okay, so again, recall this Hamiltonian where basically we apply spin-spin interaction during the first half of the period, and then we apply Pauli X rotation during the second half of the period. So due to the simplicity of this Hamiltonian, we can explicitly write down the one period time evolution operator, also called Floquet operator, simply as a product of two exponentials, as we can see in this equation 5. And we can massage this equation a little bit to recast it in this form. Okay, so for example, we can, because these two terms commute, we can separate them into different exponentials, and then we notice that this ZZ interaction forms the stabilizer operators for quantum repetition code. So we can identify this the exponential associated with this ZZ interaction to be the repetition code Hamiltonian. And then similarly, we can also massage this first exponential by expanding h around the value of pi/2, the perfect 180-degree rotation. And by using Euler formula, we can see that when h is exactly pi/2, then this exponential will reduce to just xj. So in that case, this first exponential will become a product of all Pauli x's. And if you remember this review slide, the product of all Pauli x basically corresponds to a logical x. Okay, so in that case, we have this logical x, and then the deviation from pi/2, the perfect 180-degree rotation, can be regarded as a perturbation that I highlight with red here. Okay, so now let's ignore the red portion for a while and just look at the rest of the terms. Okay, so it turns out that we can diagonalize this unitary exactly, and in particular, all the eigenstates will be of this form, will be a symmetric or anti-symmetric superposition of two product states. So here in equation 6, I give you just an example of what I call the logical Floquet eigenstates, which are basically superpositions of logical 0 and logical 1 in the quantum repetition code language. And the quasi-energies, which are defined as the phase of the eigenvalues of the unitary, can also be explicitly obtained here above equation 7. And one crucial thing to notice here is that the two quasi-energies are separated by pi. So physically, we can understand what happens in this system from this picture. So basically, we have a if there is no driving, basically we have a repetition code Hamiltonian, and we know that for a repetition code Hamiltonian, all the eigenstates will be twofold degenerate. And then in the presence of this periodic driving, then this degeneracy will be lifted, and all the quasi-energies will form as pairs that are separated by pi in quasi-energy. And as we will see in a moment, this pi separation is very crucial to establish the 2T periodicity in this existing time crystal models. Okay, yeah, so to understand this, let's take a look at the random initial state. So for simplicity, let's just look at this 0, 0, 0 state, so the logical 0 state. So by comparing with equation 6, we can see that this state can be written as a superposition of these two Floquet eigenstates. Okay, and then now let's look at what happens to this state after one period. So in that case, the time evolution of this state can be obtained by applying this unitary to the state. But by okay, and then we can expand this state using these two Floquet eigenstates. But by construction, this unitary acting on the Floquet eigenstates will give us this phase in equation 7. And especially we notice that because the two quasi-energies have a relative phase of pi, then we have an extra negative sign here. And again, if we compare with equation 6, we notice that the previously symmetric superposition of these two Floquet eigenstates become anti-symmetric superposition of the same two Floquet eigenstates. And this actually corresponds to the logical 1 state. Okay, so we can see how the spin orientation flips from up to down here. And then repeating the same argument after 2 periods, then the system returns to the original. Okay, so in that case, we can see how the pi of the relative pi phase plays a very important role here to establish this 2T periodicity. Okay, any questions so far? Okay, but so far the argument that I presented has been ignoring the effect of the perturbation. Okay, but now if we include the perturbation part, so that means we assume the presence of system imperfection. So that means, for example, the spin rotation is not exactly 180 degrees. Then the 1 period time evolution operator, as we have seen earlier, can be written as a product of two unitaries, one of which represents the perturbation, and and the other represents the original, I mean the ideal one, the ideal unitary. And then if we consider 0, 0, 0 state as our initial state, then applying this time evolution operator to the state, and then using the result from the previous slide, we can see that basically we have this u prime multiply this logical 1 state, Okay, and then we can rewrite this state in terms of the Floquet eigenstates of the ideal unitary. Okay, we can do that because of completeness. In particular, we want to especially focus on these two states from earlier. So this epsilon 0 plus minus. The idea here is that if we can show that these coefficients have a relative phase of almost pi, then the 2T periodicity should be maintained. And that is actually the case, right? Because this u prime can be written as this exponential. And then we can use Euler formula to further expand this exponential as cosine and sine. And then if this imperfection is quite small, then we can actually show that this relative phase is indeed pi up to an error of order epsilon to the power of n. So in order to understand this, basically you can imagine that there are only two things that will make this overlap to be non-zero. So the first thing is that when u prime is identity, in which case epsilon 0 plus hitting on 1, 1, 1, 1 will give you a +1, whereas epsilon 0 minus hitting on 1, 1, 1, 1 will give you a -1, right? That's from this definition of equation 6. Okay, and then the other non-zero contribution actually comes from x to the power of n. I mean, sorry, not x to the power of n, but I mean the product of all the physical Pauli x's, right? Because then that corresponds to a logical x. So the logical x will flip this logical 1 back to 0, and that's where we can have a non-zero overlap with epsilon 0 plus, right? Otherwise, imagine, for example, if you just look at the component of this equation 10 containing only a single Pauli x. So this Pauli x will flip one of these ones into 0. But remember that this epsilon 0 plus and epsilon 0 minus only comprise of superposition of all zeros and all ones. Okay, so in that case, then the overlap with the resulting state will be 0. Okay, so in other words, this discrete time crystal model is designed so that any imperfection, system imperfection of order epsilon, in terms of the periodicity corresponds to a logical error of much smaller order epsilon to the power of n. Okay, and for example, that's how we can see why the improvement, I mean the 2T oscillation pattern improves as you increase the system size, because the error will become smaller and smaller. Okay, so any questions so far about this? Okay, so if not, then now, oh, okay, so there is a question from Alexei, I think.
Yes, Alexei, please go ahead.
Right, yeah, could you go just one slide back?
Okay, this one?
Yeah, I'm actually curious. I mean, I'm somehow missing. So where does this, I mean, which terms contribute to this epsilon to the power n correction?
Right. So if we look at this equation 10, then there will be a term that goes as the product of all xj, right?
Yes.
So yes. So that terms correspond to a logical x, right? Because the product of all x is logical x. Yeah, that's right. Yeah. So in that case, if u prime is a logical operator, right? So that will change one logical state to another logical state, and therefore the resulting state will have an overlap with the, with this the relevant Floquet eigenstates that only have support on logical states. Right, but otherwise, then we can see that the overlap will be 0. right? Okay, so let me maybe just illustrate something. So consider, for example, just a system of 4 qubits or 4 spins. So if we look at the term of equation 10 that contains only x2, so this will be transformed to 1, 0, 1, 1.
Yeah.
Okay, however, remember that this epsilon 0 plus minus.
No, I remember. Yes, it only contains logical 0 and logical 1.
That's
so that's
right.
Precisely. I mean, okay, let me just go. I think what I'm missing is that I have the impression that, I mean, I'm struggling to understand why there's even a correction, because it looks like that U prime, well, basically for this scalar product, epsilon 0 plus U prime logical 1, I mean, the U prime, the only term from the U prime which give any contribution are actually the terms where you just have the product of cosines or just the product of all signs.
Exactly, that's right. That's right. And all the product of all cosines.
Yeah, so let me explain. So the trouble I'm having is that, to me, then, I mean, I think I'm missing, well, I definitely missed something. I simply don't see why there should be a correction at all. So that's what I'm struggling with.
Why is that?
So I understand why the phase pi is there. Because you have the difference between epsilon 0 plus and epsilon 0 minus. But why is there correction? That's what I do not see.
Okay, right. Yeah. So I mean, again, as you mentioned, the non-zero contribution comes from cosine to the power of n and sine to the power of n, right? And then if we just look at the like the sine to the power of n term, which contains the logical x, right? Then logical x acting on this 1, 1, 1, 1, for example, will give you 0, 0, 0, right? But remember that these Floquet eigenstates contain a superposition of 0, 0, 0 and 1, 1, 1. So in that case, you see that this will have non-zero overlap with this, right? So
yeah, so you mean, so these products of sines and cosines would be the origin of the correction?
That's right. No, actually just the product of sine. I mean, the product of cosine will actually give you this part, right? The pi part.
Okay,
because
well yeah, I mean, I now understand where the correction comes from. So yeah, thanks.
Okay, that's good. All right. Okay, no worries. Yeah, any other question? Okay, let me just erase this. Okay, so now I can present how, using this insight, we can generalize the idea to construct any 2 to the power of n T periodic discrete time crystal. So the idea is that, well, in this case, you will obviously need more than just one repetition code, right? Because just now we see that with one repetition code, you can create a 2T periodic time crystal. So now imagine we have n copies of quantum repetition codes. Okay, so in this case, the resulting Hamiltonian will the eigenstates will be degenerate, will be 2 to the power of n-fold degenerate. Okay, and then the idea is that rather than so now we look at the unitary directly. So we don't look at the Hamiltonian first. So we just look at the one period time evolution operator. So the idea is that rather than having this logical x, because from the previous analysis, we see that this logical x is the one that plays a very important role to establish the 2T periodicity. Okay, so rather than having a logical x operator, we instead consider another quantum kit that results in the splitting of all these energy eigenstates to quasi-energies that are separated by a value of pi over 2 to the power of n minus 1. So the idea here is that if you can see from my derivation earlier how a relative of pi phase generates 2t periodicity, hopefully you can see that a spacing of pi over 2 to the power of n minus 1 generates 2 to the power of n t periodicity. Okay, and it turns out I found that such a quantum gate operation that can do this is this combination of a logical Pauli X acting on the first quantum repetition code, followed by a product of generalized CNOT gate acting on the rest. So yeah, so to give a clearer example, let's just look at the construction of a 40 periodic discrete time crystal. So that means, again, we don't look at the Hamiltonian first, we look at the Floquet operator. So we want to first realize this, we need 2 repetition code firstly, and then we realize this exponential that basically describes the evolution of the repetition code Hamiltonian associated with the 2 codes. Okay, and then followed by this logical quantum gate. And it turns out that at the level of the physical qubits, we can realize these 2 quantum gates, the Pauli X and the CNOT gate, as these terms. So in that case, now if you want to come up with a Hamiltonian, for example, we can consider a 3 time step Hamiltonian, whereby during the first third of the period, you apply a ZZ interaction, just like the normal 2T periodic time crystal. And then during the second third of the period, you apply this term. And that means that the Pauli X rotation only on the first quantum repetition code. So, okay, so basically each quantum repetition code here is represented by the 2 chains. So the first chain here corresponds to 1 repetition code, and then the bottom chain corresponds to another repetition code. So yeah, as you can see, this term can be realized by applying Pauli X rotation only on the first quantum repetition code, and then during the last step before 1 period, you apply this more complicated terms. But this more complicated term is actually also doable, because you can see that it comprises of only Pauli X, single Pauli Z, as well as this XZ interaction. Okay, and then we can see the dynamics of the system in the spatial case when all the spins are aligned in the positive Z direction in the right panel of this picture. Okay, so yeah, any questions so far about this example?
Yeah, can I ask? So this is somehow like you have 2 chains, right? And
that's right.
In a sense, it's like doing kind of 1 2T discrete time crystal up on the upper chain and 1 2T in the lower chain, and the other one is kind of just waiting. So you kind of double the 2T periodicity of the whole system. But this simpler example doesn't give you the kind of robustness, right? The extra robustness.
That's right.
that
yes,
you
that's
get with
right.
your,
yeah, exactly.
But the
right.
simplified idea would be this, right? Your version
right.
just gives you this extra epsilon to the n robustness, right?
Yes, that's right.
Mm-hmm. Okay, thank you.
Okay, all right. Yeah, so so to numerically verify this theoretical analysis that I did, I also have plotted some pictures. Okay, so basically the left and the right panels correspond to the average magnetization for a spin, for a system initialized in all positive z direction. And then the left panel corresponds to a system size of 4 by 2 repetition code. So that means each repetition code is of size 4. And then the right panel corresponds to a size 5 repetition code. So in both cases, we can see that the 40 oscillation, because we want to have a 40 periodic discrete time crystal. So the 40 oscillation is very clear, both at short time dynamics as well as at the long time dynamics. And moreover, when we compare the long time dynamics, we can see that the 40 oscillation in the size 5 chain is still persisting as compared with the size 4 chain. Okay, so this verifies the fact that the increasing the system size improves the performance of the time crystals. And then basically the panels C and D show the corresponding Fourier transform for the short time dynamics. Okay, so they are roughly the same because the short time dynamics for both system sizes are very similar. Okay, and especially we notice a very sharp peak around 0.25 omega here. Okay, so omega is the frequency of the driving. Okay, and then in order to realize my construction, I also propose the possible realization in the sycamore device. Okay, so this is not straightforward because in the actual sycamore device, you cannot just create any quantum gate operations you want. Okay, so in this case, we have to build all the quantum gate operations that I proposed earlier using only the native gates of sycamore device, which are basically the I-swap gate and single qubit rotation. Okay, and then yeah, basically the quantum repetition code part is described by the circuit labeled by A, and then the Pauli X rotation is by this circuit in panel B, and the interaction, the intercode interaction part is described by this circuit in panel C. And then I also did some numerical simulation, and to make things realistic, I also assume that all gates are in fact imperfect with an error of around 0.5% for single qubit rotation and 2% for I-swap gate to match the realistic condition. Okay, and this is in addition to the parameter imperfection that we intentionally introduce to the system. Okay, and as we can see here, the 40 oscillation signal is still very clear, and this the lower panel shows the Fourier transformation. Okay, so now the main lesson of what I have explained so far is that basically we can use the concept from quantum error correction to create new flow gate phases. Okay, and some future iterations that can be done, for example, is that we can try to explore other potentially new phases of matter that can arise if we just apply the same construction that I just presented, but using other quantum error corrections. Right, quantum repetition code is not the only quantum error correction that exists. There are other more sophisticated quantum error corrections like surface codes, color codes, and so on. And in fact, I actually have a follow-up paper already published in PRP along this direction. So if you are interested, you can actually check that PRP paper where I construct a new type of time crystal called a non-local discrete time crystal using surface code rather than quantum repetition code. And then even away from time crystals, we can also imagine constructing other phases of matter like parafermion phases. Okay, so this direction has also been explored by me also in my latest preprint that you can find this archive. So it's currently under review in PRP also, the second round. Yeah, and then more ambitiously, the existence of new flocate phases that arise from using this quantum error correction machinery can further be utilized maybe to do some useful quantum computing. Okay, so for as one possible future direction, we can imagine, for example, the potential realization of flocate phases that can host very exotic quasi-energy excitations like Fibonacci anyons, which are known to be able to do universal quantum computation. Okay, and if you are interested to know more detail about my paper, you can check out this archive. Okay, and with that, I end my presentation. Okay, so thank you.
Thank you, Raditya, for this wonderful presentation. Let us thank our speaker. And we have time for questions. Sergey?
Yeah, I'm still waiting for others, but maybe if no one else raises their hand, let me start with some, okay, a simple question, I guess. So these error correction codes, I'm trying to understand. These are unitary operations, correct?
You mean the code? No, I mean the quantum error correction code is a procedure, right?
Right. So
are you talking about this quantum? I mean this repetition code Hamiltonian, or like?
Well, you explained that you use this error correction in order to reduce the error. So you have a small deviation epsilon, which then becomes epsilon to the power n.
Right. Okay.
And that, so to say, diminishes the error. Basically, gives you stability, if I understand correctly.
Yes, that's right. That's right.
So when you implement this, the implementation of this scheme, can you repeat that maybe again in simple words? Is that a unitary operation on your quantum system?
Well, yes, because like, for example, this time periodic system is described by a flocate operator, right, which is a unitary operator. And this flocate operator, for example, if you just look at the 2T periodic discrete time crystal again, comprises of two exponentials, and basically we can attribute like one of the exponential to be representing the stabilizer operators of a quantum repetition code. So in a way, we can understand like the stabilizer part to be the one responsible to do the quantum error correction. And
so that
then,
is some kind of Hamiltonian which acts during a part of the time.
That's right. Yes, that's right. Yeah.
Mm-hmm.
Yeah, so that's why we split the Hamiltonian into several time steps. So basically, the idea is that we want during one of the time steps, we want the Hamiltonian to realize the stabilizer operators of some quantum error correction codes, and then during the other time steps, we want the Hamiltonian to generate a unitary evolutions corresponding to some quantum kits that can create the periodicity that we want.
Mm-hmm. Okay. So, right, why I'm asking is the following, that, I mean, Period doubling is something which is quite standard in non-Hamiltonian, let's say, settings, or maybe even in driven classical systems, or
that's right.
Right. And so I was always a bit wondering what this when this the time crystal studies started to pop up, what the connection is to the period doubling bifurcation scenario from let's say nonlinear dynamical system, and maybe also to these Arnold Tongue and similar things which we know from, well, these are basically just linear driven oscillators, parametrically.
Yeah, I mean, I understand your question. Yes. So, well, there were actually some studies which show that actually, even including one of my earlier time crystal paper in 2019, which basically show that in the classical limit, so that means if we apply some mean field approximation to the interaction, then we can make a connection with this period doubling in the quantum chaos language. So I mean, in a way, the period doubling scenario can be understood as the as some classical limit of some time crystals, I think.
Right. Yeah, so, but in a lot of cases, this period doubling, well, it depends. I mean, you can get period doubling scenario and bifurcation scenario in all kinds of settings, Hamiltonian and non-Hamiltonian settings. So are you here referring to the Hamiltonian ones?
Yes, the Hamiltonian ones. That's right. I mean, because we have a Hamiltonian here.
Thank you. Other questions?
Let me ask a very basic. I don't know what a sycamore device is. Can you just
explain?
Sorry,
right. Sycamore device is a superconducting chip, basically developed by Google earlier last year, I think. Yeah, there was a paper in Nature by Google. I think you can just Google it. Just Google Sycamore device, then you can see like the paper.
Well, who was the author? I mean, certainly not Mr. Google, because right. So which
no, I mean
lab? Is that the Martinez lab? Or was that?
Yes, Martinez is involved. Yeah, Martini and his collaborators. I mean, there are a lot of authors there, but I mean, all the authors are affiliated with Google.
I see. Okay, I think we have some questions here. Dilip, you first, please.
Basic question. For example, like
louder, please. We don't hear you well.
Sorry, can you hear me?
Not very well. I can't hear you very well.
Okay.
Closer to the mic, maybe.
I am having this full sound.
Okay. Try it.
Yeah. So can you hear me now? Not really, right?
Not really. Lower left, where you have mute, you can find audio settings and increase the volume.
Unmute them, yeah.
Okay, then just try to be as close as possible to the mic, and we'll just try to listen.
Yeah. So still can't hear, right? So, but maybe a little bit something crazy. Yeah, I don't know.
Go ahead.
Yeah. So I have just one question. Like, for example, like when you said like about this logic get input, for example, you have taken 0 as the 0 stuff, and then 1 as the fully ferromagnetic ordering stuff. But can you start with like from anti-ferromagnetic to ferromagnetic kind of 0-1 state? Like if you take like anti-ferromagnetic state as the 0 and 1 as the ferromagnetic 1, so then how this time translation or time periodic stuff will go? Is it kind of totally different or something not so interesting? Could you follow this?
Did anyone hear the question? I mean, I can't hear
Not really.
anything.
I think, Dilip, please, there's some problem with your device. You maybe want to check it later, but right now, just maybe you can write your question in the chat and then we can read it. Okay, would you please do that?
Yeah,
and in the meantime, we switch to Alexei. Alexei, you also had a question, please.
Yeah, well, I had a very simple questions. So the examples you've showed in your talk, they all basically play around with time crystals with period double 2t or 2 to the power nt. Any ideas on how you can make period 3t?
Well,
or
yes,
say
I mean,
5t?
that's right. Well, yes. Yeah, in principle, we can actually create any periodicity and not just 2 to the power of nt periodicity. I mean, the key idea is that we want to choose the quantum gate operation appropriately. So this part. So the reason why I only mentioned 2 to the power of nt periodicity in this presentation is because this class of periodicity can be realized using this this quantum gate operation that I presented in equation 12 here. But for example, in my arXiv paper, I also showed the case with 3T periodicity using another choice of quantum gates. Yeah, so it's possible to create any periodicity actually.
Okay, thanks.
Okay, I think we have here now the question from Dilip. So let me read it. Can we take 0 and 1 states to be the antiferromagnetic ground state and ferromagnetic state respectively? You can also read it.
Oh, and by the 0 and 1 states, you mean the logical states? Is that what you're saying?
Well,
yeah,
that's
right. Yeah.
I mean, yeah. So
Saying
I mean,
yes.
I guess that's the question. So maybe let me just rephrase the question here. So yeah, so in this so in this particular example, I define the logical operators to be all zeros and all ones. So perhaps the question is it possible to define the logical 0 to be like an antiferromagnetic 0, 1, 0, 1, and then the 1 state to be 1, 0, 1, 0 states, I suppose then?
Yeah, right, yeah.
Now I look at the question again. So you are saying 0 state to be antiferromagnetic. So that means the 0 state would be 0, 0, 0, and then the 1 state would be 1, 0, 1, 0, something like that. No, that cannot be done because then, for example, they do not diagonalize the stabilizer operators with the same eigenvalues, right? With the same set of eigenvalues. But what you can do is to have something like, for example, 1, 0, 0, 0, 0, and then 0, 1, 1, 1, 1, 1. I mean, if that is the case, then the two states here will still diagonalize all the stabilizer operators with the same eigenvalues. But the main difference with this definition in equation 2 is that S1 will be -1 rather than +1. But it is fine to redefine the logical PC state this way as long as everything is consistent. Yeah, but the crucial point is that you want these 0 and 1 states to share the same eigenvalues for all the stabilizer operators.
okay. I think Dilip is satisfied with the answer and says thank you. Alexei, do you still have a question or you just forgot to lower your hand?
Just forgot.
Oh,
I have a question.
mhm.
If I understood correctly, so all of these proposals to go beyond two-time periodicity, the main plus kind of is the robustness that you bring in, if I understood correctly, or is there something else? And I mean, yeah.
Well, I mean, in order to call a particular system to be a time crystal, then we need the robustness, right? So basically,
sure.
what I've demonstrated is that we can establish this robustness by using some technique from quantum error correction code.
But still somehow your proposals are more robust than the previous ones, or the ones that were also experimentally demonstrated.
No, okay. So
what, how does
I
it
would
compare?
say is that, I mean, my proposal generalized the previous one, because, for example, my proposal here actually also includes the previous one, right? So like as we can see in this slide, so this model, this Hamiltonian, is basically already studied in the previous papers as well as realized in experiments. Only that I re-explain like the mechanism behind why this Hamiltonian is working as a time crystal, using the language from quantum error correction, right? So that's why earlier I identified this ZZ as repetition code Hamiltonian, this part as a logical X, and then later on I continue using the same language to generalize this construction to higher periodicity situation.
So the epsilon to the power of n is already incorporated in the experiments somehow, the robustness.
That's right. But only that particular explanation was not used before. So that's the new thing.
Okay, then why would you need or I mean it may be a nasty question, but why do you want 3T or 4T or larger? I mean, one would expect that you want to do things as fast as possible, right? So the 2T is kind of the fastest. So what is the kind of...
No, but I mean, it's just
bonus
because time crystals in general should be able to host not just 2T periodicity dynamics, right, but all kinds of periodicity, right? But so far, all the existing experiments can only realize 2T, right? So basically, we are missing something. We are missing something.
Sure. So you're expanding the family of time crystals.
That's right. That's right.
Possible phases. Okay. Okay. Thank you. So do we have any further questions from the audience? I do not see raised hands. So in this case, let us thank Raditya again. And with this, we conclude